in this example, the propulsion or rocket example, we are asked to use the ideal rocket equation to calculate the amount of propellant FishySat must burn to complete the plane change maneuver. Now, there are a lot of details spelled out in this paragraph, but what we really need for this problem is that the delta V is 4.58 kilometers per second, the ISP is 2,500 seconds, and that the initial mass is 350 kilograms. So we'll use the ideal rocket equation, which is in the propulsion section of your equation sheet on the front side, right column, almost all the way down. And that equation is that delta V is equal to ISP times gravity times the natural log of mass initial over mass final. We know mass initial is 350 kilograms. The only difference between mass initial and mass final is the propellant. So mass final is equal to mass initial minus the propellant, and this is what we're looking for. So when we plug in our variables here that we're given, we have 4.58 kilometers per second is equal to 2,500 seconds times gravity, and instead of using 9.81 meters per second squared, I'm going to convert it to kilometers. So it's 0.00981 kilometers per second squared times the natural log of our initial mass, which is 350 kilograms, over 350 kilograms minus mass of propellant, which is what we're looking for. I'm going to move these two terms over here. Before I do, this second will cancel the square, and my denominator will also be kilometers per second. Now these units will go away, and on this side I have 0.186748 I want to get rid of this natural log, so I'm going to use the natural number e, just like we did on the FSE. So I'll raise both sides to with the natural number e. And those cancel. This ends up being 1.20532 is equal to 350 kilograms over 350 kilograms minus mass of the propellant. I'll take this denominator and multiply both sides, and I'll divide both sides by this, which leaves me with 350 kilograms minus the mass of the propellant, this whole thing, is equal to 350 kilograms divided by 1.20532. Running out of space, let me just move up here. So then 350 kilograms minus mass of the propellant is equal to 290.375 kilograms. I add mass of propellant to both sides and subtract 290.375 from both sides, and I have 350 kilograms minus 290.375 kilograms is the mass of the propellant. So that's how much propellant would be needed to complete the plane change maneuver. So the second part of this problem says if the FishiSat is carrying a maximum propellant load of 100 kilograms, what is the delta V maneuvering margin? So it tells us right away that the total required is 6.5. We want to know what the margin will be when we have a max propellant load of 100 kilograms. So again, from up here, mass final is mass initial minus propellant. If we have 100 here and our initial is 350, our final must be 250. Okay, we had an initial of 350. Our mass of the propellant, the maximum used, is 100. 350 minus 100 is 250 kilograms. So again, using the ideal rocket equation, delta V equals ISP, gravity natural log of our initial over our final. We have that the delta V is equal to the 2,500 seconds, gravity 0.00981 kilometers per second squared, times the natural log of 350 kilograms over 250 kilograms. The second will cancel with these. Our kilograms here will cancel, and we'll be left with kilometers per second. Multiplying straight across, we end up with 8.2520 kilometers per second. So that's what we're capable of, and we want the margin. What is the margin? Oops. Delta V required is our margin. So we have 8.2520 kilometers per second minus what's required, the 6.5. So we are left with a margin, a positive margin, of 1.752 kilometers per second.